Hey, Peter. Is it just the two of us now?
It
Uh,
is actually, yes.
is,
Um,
is it? I forget. Is it? Did we decide that this class was going to be optional or something? Or well, I mean, every lecture is optional, but
yeah. No. Actually,
oh,
I was
people are
talking with
turning up. Yeah.
like one or two people who was like, oh, uh, they was like, oh, I'll probably show up next thing, and I was like, okay, but I don't know.
All
I
right.
think
Okay.
people are
Well,
just slow.
I
I think
hope.
it's a slow day or
Yeah.
something.
Yeah. It's raining and cold, I guess.
Hmm.
But what was I going to say? Um, um, yeah. People are starting to show up. Yeah, I was just wanted to make sure that the format of our last class didn't turn people off. Where I basically stepped to the sidelines and you guys were basically driving the car or the train. It was really good to watch. I took a look at the video and it was really nice. So thank you all, Nate and all these guys. Let them all come here, and then I can give you some more feedback, because that's really a great way to become successful software engineers in out there. I think is to be able to work with all stripes of people, because just be able to see the value they bring to the table, because everybody has faults. And if we just occupy our time looking for the bugs in other people's the flaw in other people's logic, yeah, we'll find lots and lots of it, right? And it's really not worth our time, because we just identified something that doesn't work, not doing anything at all, right? So I think being able to spot what the value is they bring, despite superficial bugs, who cares, right? But being able to spot the value, no matter how they bring it, right? No matter,
Hmm.
it's like a rose bush is thorny, but it does have a rose in it, right? So um, being able to identify and just being able to work with other people at the ideation or the idea or the thought level, right? Because when you're working at the intellectual level with other people, everything else fades into the background, right? What they look like, what they speak, what they believe, with their worldviews, everything gone out, right? Because at that point your intellect is interacting with their intellect, no matter, right? They could be children, they could be adults, they could be professors, anything, parents. But if you get to the level, if we're lucky enough to get to the level of interacting at that level with someone else, I think great progress can be made. By a person who's able to do that generally. And I think this is a great practice run for us, right? Because you guys actually had a chance to interact in this class where even unlike the UCs and the other colleges, where you have the population, the student population that enters the college is somewhat curated, and through SATs, and it's kind of normalized, right? Whereas in community colleges, in America, right? In the States, the philosophy is slightly different, because it's geared directly towards education, right? Education is basically knowledge that's available for free. So the only money you pay is really for the upkeep of the staff and things like that, really, right? You don't pay like 2K bucks to a university, right? The community college classes, sometimes better quality, right? So sometimes even better quality, because of course you see a huge variation. Just because we say education is available for free, anybody who wants to teach, someone who has a great skill and someone who wants to teach, welcome to come and teach here. And anybody who wants to learn can learn. So on both fronts, you will find a huge variation, just like in real life, right? So there will be fantastic instructors gelling well with your way of understanding things, and other instructors who have completely different ways of teaching, you don't even relate to, right? So, but you have a huge variation in community colleges in the States, and that's a beauty, right? Because that comes from just saying the value is on education. right? Not on the certificate, not on all these things. What we want is basically to say that, if you are good at something, so which means that, students also come in different stripes, and we welcome all students, right? We can't say that, only students who have got this level of IQ, even if that, makes sense, or only people of this particular elite brand, the standard or status can participate in this class. And that's not a good class, because it's actually setting an artificial standard, because it's saying, what I'm teaching is not knowledge. It is something that can be valued for money. Right? If it can be valued for money, no matter, even if it's $10 billion, yeah, okay, it's a finite amount, right? It's 10 billion, it's worth $10 billion, right? You put a value on that piece of knowledge, and if it's going to cost me $15 trillion to get that piece of knowledge on a piece of paper signed by the president of the world himself, right? That's great. It's worth $10 trillion, but it's only worth $10 trillion, right? Because it's got a finite value. But that's not the approach taken by the community college education system in America, which I absolutely love, really, because it gives people a chance to do what they love, and at the same time give them a chance to infect other people with the germ of pleasure that comes from pursuing any of these fields, right? So and for no cost, you can just come and enroll. And in fact, if you enroll in my courses, you even get a chance to get your fees back, right? Plus $80, right? If you are the most helpful member in the Reddit forum, someone could vote. Oh, by the way, is it week 10? Is it week 10 or week 11? This is week 11, is it?
Ooh, I don't know.
No, this is week 10.
Week 10, okay.
Because we got lectures next. Yeah, we got lectures next week. Yeah, thank goodness.
Yes, we do.
Yeah, this is Thursday. I keep thinking, I keep getting these Tuesdays and Thursdays mixed up. All right, so it's Thursday, which means next week is week 11. So we have an entire week to talk about pointers and, linked lists and manipulations, things like that. Today, what we'll do later on today is do stacks. In fact, what I'm thinking is that the way we can do this is yeah, okay, all right. Yeah, so the way we can do this, I can talk about stacks as much as you guys want, where they're used, different kinds of stacks, and the size, and how to find the size of the stack you get. How do you know, right? How do you know? You write a program on Replete, and then you get a runtime stack, right? So how do you know how big your stack is? Even memory, right? How do you know how much memory you're? There's ways to find out. But yeah, there's this. I can show you a couple of. I don't know if it's useful, right? So here we can talk about stacks, and then towards the second half of this class, when we can follow the same model as last class, right? So we can have the students play playground, and I'll step away within earshot, and then. Before you guys start, we'll just establish a template, right? So we'll just open a Replete or cpp.sh, establish a template, and fill in some functions. We'll create the stack class and fill in some functions, and with some comments on top of the functions. I'll guide you through that, but we won't fill in the functions. We will fill in the bodies. We'll fill in stub functions, right? And then we'll talk about how to implement these, and then I'll step away, right? And then you guys can go away and have a field day, right? Playing around with these functions, implementing them in the way the comment suggests, in another way, in yet another way. We can play around, right? And have experiment and have fun after that. And then I can come back in the last 10, 15 minutes. I can come back. You can just call out to me anytime. Does that sound like a plan?
Sounds like a good plan.
Great.
Yeah, sure.
Yeah, sorry. You were saying, Nathan?
Oh, I said, yeah, sure.
Yeah, great. And by the way, I was going to say thank you all guys for driving last class. It was fantastic. Oh, that's how we started talking about all this, right? Yeah, and I think the reason why last class, I was very pleased to see last class, because like I say, in community colleges, because the student population is not already curated into to be kind of cohesive, we have a variety of mix of students, right, who bring different levels of expertise, different levels of knowledge, different levels of previous experience, and interest, different levels of interest, right? Because you have different ages, and some people might say today, right now is the time I have to learn C++ because I have to do these things in C++. So another person might say, well, what's all this big news about C++, I got to find out more about it, right? So it's more superficial. So you have all these people, and driving amidst those that group is also practice, right? It's practice, because you got to learn to interact not just with a curated bunch of people who are good enough to work with you, but you got to learn to see what's good in everyone, right? Because because you actually were using good stuff that everybody was saying. Everybody's saying good stuff and bad stuff, and you're all queuing in on what's good and what's bad, and let's try it out, and so on and so forth. And I think that is a fantastic skill, which is really not taught formally in classes in C++, in software engineering classes too, because it's not only a skill in software engineering, even in life, right? Because like we were talking before, right? So in software engineering, in teams, then you get to be a really good contributor to a team, whether it's a team contributor or an individual contributor, or even when you later on have to manage other people, right? And manage a team, how to easily find the value, right? And not find the fault, right? Because finding fault is a waste of time, and at the end of your life, you'll regret it, right? So, but finding value is actually a great thing, right? It's because it's fun. It enriches your own life, enriches what you want to do. So I think it's good to train ourselves, because it's not easy. It's not easy to find value, right? Even diamonds, right? It's the diamonds hidden inside of rocks. You got to chip away and and finally polish it and get the diamond, right? So finding value is really hard. Finding rubbish is easy. So lots of people go around just finding rubbish and say that's wrong, I'm superior, I'm better, better because of this, right? And that's all nonsense. That's because they don't have the ability to find value. And so this class is absolutely fantastic, and I think we should use that example, right? So you should refer to the class that you guys drove on YouTube, link it up to your friends and say, that's a great way in which you can drive class and do something really cool, and find value in everything. All right, so let's talk about stacks. What time is it? Yeah, 8:15. Yeah, good. All right, this is around when we talk about serious stuff, right? Okay, stacks. Yeah, I'm happy to. Before I start talking about stacks, if you have any questions, either about I assume at this point that you guys are. Where's Ben? Is Ben here? Oh, Ben's not
Yeah,
here.
it looks like.
Okay, I got to reach out to him, right? I hope we didn't scare him off, because he comes to this class, like I said, from a design background, right? So he's a designer, and so, but those are the kinds of people who can really bring value to computer science, right? Because computer science is really enriched. Well, at the end of the day, computer science is a means, right? It's just a chisel and hammer. It teaches you how to do things, but what good is the tool? What good is the means if you don't have something to accomplish using these means? Right? So that's why computer science, you should learn computer science really well, but the value in computer science comes from all these other people, all these other skills that we bring to bear, like artists like Ben and all these people who learn the tools, and then they can do something mind-boggling, right, with these tools that they've learned in that field that they're already good at. So those are the kinds of people we want to attract and rein in, right? And we got to be like super duper nice to them and keep them in, make sure they don't leave, that kind of thing. And so yeah, so we got to reach out to him and see what the hell is going on. It'll be a pity, because he's interested in design, and obviously he can do things like in Unreal, automotive, right? So many things that he can do. And so yeah. So those are the kinds of things. Yeah. Sorry, go ahead.
I once worked with someone who had a PhD in music.
I'm sorry, I can't hear you.
Effective analyst.
Aaron, you're cutting out a little bit, but I think I get the gist. You're talking about somebody who had a PhD in music, who coded something along those lines.
Yeah. Mm-hmm.
Okay. I can hear you. Someone's chopping away. Or doing something.
Was a very effective analyst. Like more than a. Oh my.
Who's talking? Yeah, Aaron,
Yeah,
Aaron,
to put it bluntly,
your mic really
as
sucks.
Matt says,
Yeah, your mic sucks. Yes. All right. So you got to communicate by chat if you want. Okay. Yeah,
your internet signal's probably not that
how
good
can you
then.
not? Mics have been perfected for such a long, well, not perfected, but I'd be surprised if the hardware and the mic. Yeah, it's your internet signal is really bad because it's corrupting your audio. Yeah, okay. You can participate by chat. Hey, anybody else, got something interesting to say or ask about stacks or ask about stuff that we've already talked about? It's fine. If not, what we'll do is, talk about stacks and what stacks are. I think someone last time mentioned Philo or LIFO. Yeah, so we'll talk about those things. And then eventually get to implement a stack. Right, what time is it? 8:20. So I think we should start implementing a stack no later than 9 o'clock, right? Maybe even 8:45. Yeah. I think we should implement a stack at 8:45. Start implementing a stack at 8:45, and then I hand over it over to you guys at 8:50. Right? So 8:45 to 8:50, we can put the template, not the template, the shell code, the scaffolding of that code together with the comments and everything.
Well, and I was gonna add, I know personally, I understand just of how a stack works. But I think it would be really useful to know some of the utility functions that we can use, like that are built into
into the stack class.
Yeah, like something like is there like a sort function, or just in general, like what functions or what general functions are that are commonly very useful? Like you use them a lot often.
Sure.
And um yeah, I guess like what their purpose is for some of these more
Absolutely,
common ones.
yeah.
Obviously we don't need to break down everything in the stack
No.
class.
I think we will break down every single thing, because the stacks really is a CS2A material. That's we'll do everything to do with almost everything. Let's say 99%. It's very simple. Really, it's simple because stacks don't have a lot of operations, right? You said, what are all the functions and methods attached to stacks? The beauty of these data structures is that they don't have a lot of these data, primitive data structures, right? So if you look at a more complex class that's created for a specific purpose, right? From Docker or Unreal, those classes, they have a lot of functions, like jQuery, and you got to memorize, or not memorize, no, right? So, but these primitives like stacks, lists, queues, they have like, I don't know, I'd be surprised if you get more than 10 functions, more than 10. They're called API calls, right? So even a vector, you can do more things with a vector than you can with a stack. So we'll do everything, and hopefully, thanks to you, we'll also implement all of the functions. Every single one of those functions we'll implement, and we'll talk about why we need the function and how and what the utility of the function is. Yeah.
Cool.
We'll
That's where I always like kind of fall flat, is I'll get the concept of something really well, and then I'll go and use it. And I'm like, so is there like a thing that I can do for this, or am I just gonna have to like create my own method for this, or all the questions I have about like there's
I
like
see.
when I'm given a new tool.
How about this? Why don't we start off right away implementing the overall, not the guts of the function, everything there. And as we are typing it in, I can have an opportunity to chime in, right, with concepts, so that it's not just one huge blurt of, oh, here's everything to do, the concepts of stacks, here's where you use it, and blah blah blah. And honestly, you have no idea, right? It's just concepts floating in the air at that point. And then all of that out of the way, and then we get to implementation. No, I think it may not work as well as if we just interleave the two. So let's start with the implementation, and then everywhere I can pepper it with the concepts, right? So the same material, but instead of coming in two chunks, it'll just come in two interleaved, mixed up chunks. Is that okay?
That works for me.
All right. Well, it's just one person. If more people are okay with that, say yes in the chat window, and then
Yeah.
Yes.
Oh, I had a quick question. So when it comes
sure,
to
go for it. Who is this,
stacks,
Susanna?
yeah, it's Susanna.
Mhm.
When it comes to stacks, is it essentially whatever goes first goes last?
Yeah. No, not first. A stack is. Have you heard the term LIFO? LIFO, LIFO, or philo, and some people call it.
Last in,
Last
first
in,
out.
last out.
Yeah.
Okay.
So but anytime you want to remember, if you want to know what a stack is, just remember a stack of plates.
Mhm.
Okay, so that's basically what a stack is. A stack of, imagine it, instead of plates, you have, on each plate, you have a whole bunch of information, right, written on it.
Mhm.
That's
And
your
for-
stack. And
and-
obviously the inside guys can't be seen or accessed at all.
At all.
Yeah, at all.
So, and then I'm aware there's two functions. There's push and pop. So it's like if you're like at a buffet, right? And then have you guys ever seen those buffet plate things where you just push and you get a plate? Is this
Oh, yeah,
essentially
yeah.
the same thing?
Fresh choice. Maybe not fresh choice, but yeah. No. So you're talking about you push a plate down and it's spring loaded and it just goes and sits in there?
It sits in there and then it comes out, whatever you like push in and then you get one out, or like push and pop.
I see. Yeah. Okay. Well, no, that I haven't seen. I've only seen, really actually stacked up, not through a machine that dispenses plates. Oh, I can see that happening later on. Yeah. In some of these automated restaurants. But yeah, we'll implement those. Yeah. Susanna, is that okay? Actually, you've never taken Susanna, you haven't taken the screen in quite a while now, right?
I took it a few weeks ago, but it's been a while.
Yeah, okay. Yeah. Any of you can take the screen now if you want, or Susanna, because she already had a question. But if one of you who feels more less confident, right? Less confident, wants to take the screen, I would actually welcome you, and I have a slight preference to that you taking the screen than Susanna, if you're less confident, right? So what I mean is not less confident compared to Susanna, right? It's less confident compared to where you want to be. Right. So less doesn't mean compared to another person, right? So you have your own picture of where you want to be at the end of CS2A, and you know in your head approximately where you ought to be right now. Yeah. So if you don't think you're there yet, please take the screen, right? Please take the screen, and we'll try our best to make sure you're there already, right? By the end of this class. So this is a great opportunity, right? So many friends here, are going to help you. Everybody's been in the same boat as you, and I'm here to basically talk you through the code. You don't even have to come up with the code, right? So we can do all that. Everybody's going to talk you through the code, right? So you want to do that? Or, all right, let's say 2 seconds more. Otherwise, Susanna will basically pick up the screen. How about that? Yeah. So if someone picks up the screen in the next 2 seconds. All right. Okay, Susanna, can you take the screen?
Okay. Should I just host through Rappel?
Yeah. Rappel was a bit of an issue when it came to sharing the code, I think, because it asked for people to log in. What you can do is we can code in Rappel right now, Replete or Rappel, and then if you ever have to share this code somewhere else, share it in one of those.
Yeah, I could always just copy paste the code into
copy
editor.
and paste. Okay. Yeah, just pick it up, and what we'll do is I think we can implement a stack class, but a stack that is going to work with pointers, right? The stack on the heap, right? Not stack on the stack, right? Not stack on the stack. Right? Well, there's all interesting things to talk about, right? So we'll talk about a stack on the heap, meaning it's a dynamically allocated stack, right? It can grow as much as you heap has memory, right? As opposed to, and we'll get a chance to talk about all those interesting pieces of side knowledge here, right? Because I think in assignment 8, in request 8, still I think it's a stack on a stack, right? Because a stack class is basically an array. Is a vector. It's a vector. So it actually is on the heap, right? But you can actually have a second. All right, good. The font size, is okay. Is okay for me.
It's okay.
Yeah, it's okay for me. Everybody okay with that?
Yeah.
Okay. All right. So let's go ahead on top of main. Yeah. Let's use namespace standard. All right. Now let's create a brand new file. Let's create the stack class in a separate file. right? So, and I think this was a question that came up before, is can you do things in 2 separate files? Yes. And I think let's do it in 2 separate files. I think on the left-hand side, is this Replit? I don't know, right? I've never used Replit.
Yeah, Replit.
So, all right. So go Replit's left-hand side. Is that how you create a new file?
Yep, right over here, add a file.
Oh, yeah, okay,
what
all
type
right.
of file?
Say stack.h with a capital S, right? Stack.h with a capital S. And what I like to do, I think I mentioned this before, is even though Java is a different language, it has some nice conventions, right? So I think it's good
But
for...
why call it TMP?
Temp?
Why call it temp? It should be stack.
Oh, I think it's temp is the name it gives by default, and then you can overtype. And stack with a capital S. And the reason I say capital S is because if you think about it in Java, those of you who know Java, right? As you create a file, a public class, the public file has to have the same name as a class, yes? And it actually helps a great deal because many times busy programmers don't have the time to look inside of a file to see what it contains. So the name of the file, if it gives away the primary class it contains, is actually a great clue to speeding up the way in which we can process other programmers' files. So I found this to be a great, even our own files, right, later on. So stack.h by convention, this is a convention that we're following in class. You know, feel free to choose a different convention later on or design your own. But our convention is that if we want to define a brand new class, we'll define it in that class.h, where the class CLAS is, right? So that's the name of the class. And then the implementation of the class, if it is simple enough, it will go in the header file itself, right? If it's not simple, and we'll come across situations today, right? If it's not simple, then we'll take those implementations and say, well, it's too complex to be in part of the header file, because the header file will get included right everywhere. So let's move that to a separate file altogether, right? So an implementation file. We'll try and do all those things today because it's going to help you also with quest 8 and 9, I think. Yeah, so we'll do that today. So now what we're going to do is in stack.h, we're going to create our stack class. Okay, so our stack class, and again, concept injection here, right? A stack class is basically taking a vector. Vector is what a stack does to a vector is what C++ did to C. All right, I don't know if that's a good analogy, right? Because and what C did to assembler. Right, so or assembler did to the CPU, right? So every time you go closer to the CPU, you get immensely more freedom, right? So freedom, I shouldn't say power, right? All that power is available downstream too, right? So, but what happens is that the closer you get to the core, the center, the freer you become. Right, because all your restrictions and all these things are lost, right? Because the use of those restrictions. What are the use of those restrictions? Because what the use says, right? The CPU has incredible power, right? Incredible power to do anything, but not do anything really. But it has a lot of things. It can do a lot of things that if you don't know how to drive, you could end up destroying things, right? So because the CPU is so powerful, I mean, not powerful, right? Because it has so many nuances. It has so many nuances that are really irrelevant to downstream life, right? Because if the CPU didn't exist, the program is not going to run at all, right? It's going to die. So the fact the CPU exists is necessary for the program to run, but the program should not be burdened by the details of the CPU that are irrelevant to the existence of the program, to the running of the program, right? So what we do is say that around the CPU, we'll build instruction set, right? Which only expose a certain part of the CPU that people can use to build useful stuff off, right? So that was born, the instruction set and the assembler language, right? I don't know, this is turning out to be a mini lesson in computer architecture, right? But even assembler language, right? If you look at it, exposes too much of the CPU, right? Gives the programmer too much freedom, right? And really think about it, right? So the reason we have gotten to such incredible power, right, is because we have chosen to give up freedom, not to embrace it. Think about it, right? So what a mind-blowing phenomenon, really. Right, because the CPU has incredible power, but it has a lot of things that it can do. But if you don't know, but if you do know, it'll end up spoiling your life because you're going to be thinking about that instead of doing what is important to you. right? So what we do is that I don't want that freedom, right? I don't want the freedom to be doing a lot of things which don't even matter to me, because then I have to be mindful of those things and take up a lot of mental cycles, right? So rather, I'll give up those freedoms, let an automaton manage that shit for me, right? So that's really what we're saying. So the assembler is really a software layer, right? It says, I'll manage a lot of the CPU for you, right? And I only tell you what you can do so that your own life will be easier. So in fact, now we became happier because we gave up some freedoms. Right? It's just like, anarchy to democracy, right? So we gave up some freedom and became happier. And then the assembler too, right? It gives you too much freedom, too much freedom, right? Because, still people can program an assembler and mulch your computer, right? So then C comes along and says, well, assembler is, let you access assembler, but still, right? It will make it harder for you to access assembler. In other words, we're going to take away a bit more freedom that assembler gave you and give you C. Right, but C++ says, C gives you too much freedom. And C lets you do lots of stuff, right, which you shouldn't do. Right, C++ takes away more freedom. But otherwise, but really, C++ is not taking away freedom. We, as humans, have created C++ as guardians, right? People always say, oh, I don't like C++ because it doesn't give me freedom to do a lot of things. Or no, because us humans, we have created C++ to take away some of these dangerous freedoms, which are basically getting in our way of enjoying life, right? So we have created C++ and we take C++ and put it in place and say, all right, so C++ takes away some more freedoms and makes us happier, right? And then, we have other languages that say, all right, so more ways you can go wrong, more ways we can go wrong, right? So how many of these ways can we go wrong? And how many of these ways can we automate? Really, that's what it is, right? So at the end of the day, humanity, as if you think about humanity, right? So what are we doing, right? What we're doing is basically thinking about all of the little pain points in life, right? We're thinking about all these things that, essentially get in the way of us enjoying life, right? It's just enjoying being, right? So chilling out, lazing, right? So we take these things and say, well, that really, I'd rather be chilling right now rather than vacuuming my home. Right? Because maybe I got to vacuum my home. So we say, let technology come to the rescue. And so let's buy a Roomba, right? So this is technology. So that basically gives you 20 minutes extra to not vacuum the house and sit around and chill. Right, and so we're slowly letting technology take over things so what we're saying here is, well, let technology take over things that I don't care about, because they're getting in the way of me enjoying. So that's really what's happening to humanity over a period of time. As civilization advances, bam, 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 we knock off all these pegs, right? And so where are we going with this, right? So so a vector is a structure in C++, right? A vector is a structure in C++, and a vector gives you a great deal of freedom, right? Ultimately, we're tying all of this back to C++, stacks, right? So it's kind of crazy, right? So a vector it's not even in C, it's not in assemblers. A vector is a high-level construct, right? It's in C++, but a vector is an array. But an array gives you a great deal of freedom, right? Because you can access anywhere, you can poke around anywhere in the array, right? Bam, 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 bam. So too much freedom, right? And it's dangerous. So C++ programmers, right? Computer scientists, right? Had the forethought to say, well, you know what? People are using vectors when they don't know how to use vectors. Just because something is available, you don't go and use it, right? You need to know how to use it. And so, these people, they're only ever trying to access the top, right, of the vector at any time. They're not accessing anywhere in the bottom. So I really shouldn't be giving them access to that, or they shouldn't be asking for access to the rest of the array, right? Because if they ask for access to the rest of the array, something is wrong in their logic. So it's better for them to say, well, I don't want a full featured array. Right? I don't want the full featured array that gives me the freedom. I don't want the vector, which gives me the freedom to do any damn thing, right? So it's very powerful. The vector has lots and lots of methods. You just Google for C++ vector, you get a lot of methods. I think it's like one page, like 25, 35 methods, that many methods, right? And many times you don't even know what these methods are. You got to go and look up and but so it's because it has so many things that can happen to a vector, there's also so many things that can go wrong. Yes, so it's a problematic, and because there are so many things that can go wrong in a vector, it takes up that many correspondingly more mental cycles, right? Whether we are aware of it or not, right? The moment you use a vector, your mind, some part of your mind has already been dedicated, right? Whether you know or not, it's been dedicated, saying, okay, I'm using a vector, so I better make sure I don't do any crazy ass things that could damage a vector, right? So whatever it is you do, it's always going to be policed by that subconscious thing there, right? It's going to say, hey, you're doing that. Are you sure you want to do that because there's a vector, right? So, yeah, I don't know, right? So you'll encounter these things, right? So so what you say is that, well, you know what? I don't want these things bearing down on me all the time. So what I want is basically a vector where I've taken a vector, but I've also given up more, right? Essentially just giving up, right? So giving up more and more of these freedoms and saying, so, right, so I don't want to do these crazy ass operations on the vector. I want a special kind of vector in which you take care of all these things, right? Growing the vector and everything else, you take care of it. The only thing I want is I want to be able to stick something on the vector, and that should always go on the top of the vector, right? And when I say what's on the top, you should tell me what's on the top, right? And then when I say I want to take something out of the vector, you should not let me take something out of anywhere in the vector. You should only tell me and let me take something off the top. So that way it's just like a stack, yes? Because here's a vector, right? It's empty. Then I put the first item on it, and then I put the second item on it, the third item on it, right? But I can remove the first item until I've taken the fourth, the third, and the second, and then only I can take the first out. Does that make sense?
Yeah, it makes sense.
Yeah, so we're saying that, I'm going to take the vector, which is like, hugely more powerful than stacks. I'm going to tone it down, right? So that's why implementing stacks and lists and all these data structures is a piece of cake, and it's really easy because what we're doing there is not building something new. We're taking something that's already got a lot of stuff in it and chipping away all the stuff that we don't need. Yeah, so we're taking a vector and basically hiding it, right? Hiding it inside of our stack and saying, okay, vector, you're going to be a vector, but we're not going to expose the whole of you to the outside. All we're going to expose is just the top, right? And then I'll have a pointer to where your top is. And every time something happens, it'll only happen to your top. Whether it's putting something on there or taking something out of there, it only happens at the top. Nothing happens below there, right? Does it make sense? That's basically, and so that kind of special vector is called a stack. A stack is a vector in which you've basically just taken a stack and said, a vector, and said, I don't want 90% of the freedoms that a vector gives me. Just give me a 10% free vector, right? It is a very tight down, toned down vector. That's what we're going to implement. The only difference here is that we're not going to do it as a vector. We'll actually do it because as a vector, you're going to do it in quest number 8. Right, but here we'll do it in the heap, right? And that will also allow us to introduce this whole this concept of heap and pointers and dynamic memory, right? So that's a stack. Now, why are stacks useful, right? What are stacks useful for? Why do we even use stacks in computer science? So stacks are used in a lot of different places, and obviously later on when you implement your own data structures, right, you will find that there are lots of algorithms, right? There's lots of algorithms that you have to run on other data structures, right? So maybe you have a tree, like that. Right, you have a tree, and then you have to find some path through the tree, depth first or something like that, right? So you always descend as deep as possible and then pop all the way back and then deep again. So that's called depth first search. Instead of breadth first is like that, right? Like that, right? Depth first is like that. So and when you do depth first, you'll find that it's easier for you to use a stack instead of a vector, to use a stack to implement your own algorithm. But we won't even go into that, right? Because stacks, as soon as you know what the stack is and what it does, you'll actually come up with a stack to use anytime that you are writing anything at all where you need something like a stack. You'll basically just come up with it automatically. So it doesn't have to be for that particular application or this, right? So, but for a system, where is a stack useful, right? So and we just did recursion, right? We just function calls. So when a function is called, again, this is a little bit of computer architecture here, right? But by the way, is this okay that I talk about this? When a function is called and where the stack comes into the picture, is it okay?
It's very interesting. I've always wanted to know.
Yeah, all right, thank you. All right, is this too slow or too fast, or is it just okay?
Kind of is a little fast.
I was about to say the same thing.
Yeah.
No,
I'm like
I do
getting the
understand.
gist of it. It's but like I'm processing things a little slower than how you're talking.
Yeah, sure.
Yeah,
all right, so just slow me down. Slow me down. If
And
necessary.
also,
you
I
guys
do
go
understand
forward,
the
right?
gist of this.
I think I got into the habit, it's because of you guys, right? Really, because, I got into the habit of watching some of these YouTube videos that you guys are creating, right? And you're typing, and then sometimes it's slow, and then I put it on 2x speed on YouTube. And then I got used to watching through everything in 2x speed. Now I'm busy talking in 2x speed. Now when you play it back, you'll get it 4x speed. Right? Okay. So kind of cool. All right. So anyway, so I was talking about what a function. So when a function call happens, right? It's very important. So let's see a main. So the main method is doing something, some stuff here, right? And then it calls a function. So at that time, the CPU has to stop executing the sequence of instructions composing main, right? Not composing, well, whatever, right? Comprising main, and then at that point, it has to take a break from there. And execute some other sequence of instructions to do with some other function stored somewhere else in memory, right? Because it's not necessary that all the functions are stored contiguously one after another in main, and because functions are separate. Each one is stored in different places in memory, right? And each one is a set of instructions, like 10 instructions, 100,000, whatever, right? So a bunch of instructions all in memory in your code segment. They're all there, and each of those functions has an entry point, right? And saying, well, if you want to execute my function, you start execution at this memory address, and that's it. Basically, it basically says this is where you start. It doesn't even say where you end, because where you end is dictated by the function itself. The function itself has one instruction at the end. The compiler will generate an instruction at the end saying return. Return is a special instruction that to the compiler, not to the CPU, that says, okay, this function is done executing. Now return control back to wherever it came from, right? So in other words, here is Chad coding something up, right? And at this point, Susanna takes over. And says, okay, Susanna is going to type this function up, right? And so Chad is not, Chad doesn't go away, right? He can just, okay, well, Susanna, all right, but he's still got this to type, right? So Susanna has that function to type, and then so Chad still has that to type, right? And he typed that much, so he can just hand over to Susanna and take off, right? He just switch off the video and go, like now, right? He's not even there, right? So he can do that. So he's still got to be in frozen mode, observing, right? And when Susanna is done with her implementation, she's going to come back and say, hey, Chad, I'm finished, right? Now you can take over. And then Chad picks up from there and then continues as with his program. Now, so far, is that okay or not? I want all of you to be on the same page. As
I understand this.
Oh, Chad, you're really there. Okay, all right, good.
And I also know something.
Sorry?
So I noticed that the value of the next address after that call function gets pushed to the stack before it gets called.
Let's not worry about those details. They'll all be there somehow. We just want to know that
I put that on Reddit.
What is the bunch of information that needs to live on the stack? That's all. It doesn't matter which order or what. That is all compiler dependent. Or all right.
But you do know that's true, and I actually put that on my Reddit post. I update it as one of the reasons why it takes longer to call than to a macro, right?
I think you already posted that, right, on Tuesday.
Yeah.
All right. Good. All right. Thanks. What was I saying? Sorry. Yeah. Okay. Susanna was Chad types and Susanna and comes back. Now, what happens if Chad hands over to Susanna and Susanna is going on and typing out her function, and in the middle of that she realizes, oh, there's another module here that needs to be written that includes, I don't know, maybe it involves audio processing or something like that, and only Nate knows how to do this, right? So maybe she says, all right, I can't complete my job until Nate completes his job, right? So she calls Nate and says, okay, Nate, go ahead and complete that, right? So you can imagine how this chain goes on, right? So now, however, before Nate comes back to Susanna and says he's done, Susanna can't tell Chad that she's done. Yes? Mm-hmm. Yes or no?
Well, yes.
All right. So the order in which this has to happen is that Chad has to basically wait. He's got to enter this frozen cryo state and basically wait. And Susanna goes away, does her thing. But in the middle, she also goes into cryo state and calls Nate to do stuff. And Nate goes to his stuff, does his stuff, and then comes back to Susanna, right? And Susanna completes her stuff, but then goes back to Chad. So you can see everything happening in the exact reverse order. Now, every time, there's a couple of different things happening here, right? So when Susanna starts executing, everything that Chad remembers at that point, right? So all of that stuff that Chad has done, this part, the top part, I don't know if the fingers are right in the frame. Maybe you shouldn't really optimize that. I don't know, right? So this part, right? So everything that Chad has done, the context, that is called the context in which Chad is finding himself at the point at which Susanna is called, right? So at the point when Susanna is being called to do her stuff, Chad finds himself in a certain situation, which is a result of all his past doings, right? Oh, opening up the editor, not only in the program, within the program, right? Firing up and allocating memory, all of so that is called his context, right? His context, and together that bunch of information that completely defines the specific context that Chad is in, right? All the irrelevant stuff can go, right? Because all you need is to capture the essential bits from Chad's context to be able to reconstruct it at some point in later in time, right? So that essential part of the data due to Chad's environment, which is required to reconstruct Chad's environment when you come back from Susanna, because Susanna is now going to take on the stage, right? This is only one CPU. We're not assuming that there are multiple CPUs, right? So the CPU is the stage, right? So Susanna is going to now take on the stage, which means Chad has got to clear the stage. Yes, yes. Okay, but before he clears the stage, he can't just knock everything down, right? He's got to take a photo. He's got to take, in other words, he's got to take enough information with him off the stage at the time he handed over to Susanna to be able to reconstruct the stage exactly from a blank stage, right? When Susanna vacates, she gives Chad a blank slate at that point, right? So blank slate, and he's got to reconstruct the stage from what he remembered or what he took away from his stage at the time he vacated it for Susanna. All right, I don't know, maybe that's a too Python-like sentence. But does that make sense?
Yeah.
That's all.
I mean, yeah.
Makes sense.
It makes sense.
Right. So when Chad wants to hand over the stage to Susanna, he takes note of all the important information, right? And the important information in a program's perspective are all the local variables that Chad is using, their values, right? And the current state of the program, whatever is maintaining, right? Basically, it's just the local variables, right?
So I think that's pushed onto the stack, right?
Right. Yes. Right. So not just so that goes on to that thing that Chad is going to save, right? So that is called the stack frame, right? So Chad is going to push something on, save something called a frame, a context frame. It's called the context frame. This is a frame, and it's called a stack frame because that frame is eventually going to end up on the stack, right? So that frame holds all of Chad's local variables. Also, it holds two other important things, right? Now, suppose Chad says, going to call Susanna and tell Susanna, well, Susanna, you got to do something, but I'm going to parameterize you, right? So you're going to paint this room, but I'm going to tell you what color to paint this room, right? So I'm going to say pink or red or something like that, right? So parameter. So how does Chad get the parameter to Susanna? There's no way, right? So he's going to say that parameter is also going to go on the stack. So there's a few things he's going to put on the stack, right? Stack, he's going to say, he's going to put all his local variables, that is his context. Then he's going to put the return address, right? The return address meaning that after you're done, Susanna, right? This is the address you need to go to in order to find me. Because if you don't go back to that address, I'm not going to come back and take over again, right? So I'm going to go and sleep now, and that's my address. So that is the return address. So he says three important pieces of information I'm going to push on the stack. And why it has to be a stack, I'll tell you, right? So then you'll know, right? So I'm going to put 3 pieces of information on the stack. I'm going to push all my local variables. That's my first thing. The second thing I'm going to push, well, I don't know if it's 1, 2, 3 here. You can determine the order yourself. The second thing I'm going to push is where I need to come back to. After you're done, the address you need to come back to. This is called the return address. That's also going to go on the stack. All right. And finally, I'm going to push all of the parameters that I'm supposed to give you. That also goes on the stack. All those things I'll put on the stack, and then I'll call you. Right. And then Chad says, okay, Susanna, can you come over and take on the stage? Right. The stage is now yours because I've cleaned it out. This is a vacant stage. It's yours. Now, Susanna comes over and lays out the stage according to her own. Right. Maybe she has to, lay it out with in a particular order, desk here and so on and so forth, decorations and so completely redo the whole stage according to her own taste. Right. So that is her context. She builds her context, and Chad's context is now saved somewhere else on a stack. Right. It does that. And when it comes time for her to call Nate, what does she do? Right. She's got to do the same thing that Chad did. right? So one thing she'll do is, well, do I need to pass any? So the first thing she'll do is, well, let me take my state, which is all my decorations, all my where did all this go, right? So take a photo of everything. Right? So take that, my context, and I'm going to push it on top of Chad's frame, right? Now Chad's frame is already on the stack. Yes, he
Yeah.
pushed it on the stack before giving it to Susanna. And Susanna came over, right? And she's going to push her stack, her frame on the stack also. Chad's frame is already there. And it's just as well that it's there because Susanna's frame should not go under Chad's frame, should go above, right? Because Chad's stack frame should not get pushed down. And Susanna's stack frame is above Chad's stack frame, right? And when Susanna calls Nate, now she's got her local variables, right? Her context. And on top of that, she's going to have her return address, not Chad's return address. When Nate, when you're done, come back to this address. This is where I am, right? So Nate says, Susanna says, this is where I am. So she puts her return address there, right? On top of that, she's going to put parameters she's going to pass on to Nate, right? And then Nate comes over and takes over. Now, when Nate takes over, he says, oh, do I have any parameters? Does my function signature? Now you think back to all those function calls, signatures, and declarations. You see how important they are, right? So I'll tell you very soon. Someone remind me later. And that's right. So Nate says, oh, I need a double and a let's say a double and a pet object, right? A pet object. Maybe a pet object is 50 bytes, right? Pet object. Let's say not pet object. Well, what have we done before? Player object, right? Player object, right? Player object, 50 bytes or something like that, right? So so when Nate when Susanna says, Nate, come on over, I've cleaned up the stage for you. The stage is now yours, right? Now you take over and do things. But at that time, she's already made sure that her return address, everything has been saved properly on stack. She doesn't care if Nate comes and clobbers everything because she has all the information needed to reconstruct her stage when she comes back. Yes? Okay, so Nate comes here and says, oh, well, I need a player object that is 50 bytes long. And I also need a double that's 8 bytes long, right? And Susanna was supposed to give me that, and the way she would give me that is she would put them on the stack. So let me pop from the stack whatever is on top, right? You can't access anything in underneath, right? So on top, I know from the function signature. Now think back, there's a function signature. From the function signature, Nate function, right? Nate function. The first object is player, right? The second object is the two parameters, right? By copy, player, comma, player P, comma, double D, right? So player P, comma, double D. So from the front, now you know why the order is so important, right? Order is, and also the types are so important because Nate says in my function signature in the compiler, I had a double D, which means that I need to pop off 8 bytes from the stack for my D variable, right? So it's going to pop 8 bytes to double, right? Doubles are 8 bytes, right? So 8 bytes, that's my D variable, right? Pop. Bam, 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 8 bytes in my D variable. Now I need a pet object, right? A player object. A player object is 50 bytes. And Susanna was going to give me that too. That also must be on the stack. So next 50 bytes are player, right? So I'm going to pop them and assign it to my player, right? Now I've got all the stuff that I want. I'm going to do my job with these two guys. I'm going to do my job and then my result. All right, I've done my job. Now, after I've done my job, I need to return back to Susanna. Where do I go? Oh, the return address. Return address is also on the stack, right? So it goes to the return address, right? Is on the stack, pop off return address. How many bytes are pointers? So the return address is a pointer, right? So pop off the return address, some memory location. So okay, that's where Susanna is sleeping. All right, so I'll go and wake her up and say, hey, Susanna, I'm done with my job with the double and the float you gave me, or the player object you gave me. I'm done. Now wake up and do your shit. I'm out of here. Okay, so the whole that and obviously when Susanna does her thing, she's going to go back to Chad and say exactly the same thing. Right? And Chad is probably going to do. So that's the chain. And the thing to remember here is that this will only work. Okay, so someone said high-level overview is going a little fast. Interesting to see in motion. I don't know what it's. I don't know, guys. You got to. Oh, you said that a few minutes ago. I don't know. You just feel free to interrupt me anytime, right? And also, don't chat. You just not chat. Okay, just speak up, right? Because I can't be looking at the chat window.
This makes sense.
All right. Okay. Great. Thank you.
So, yeah, that makes sense why calling functions takes longer, I think,
Yeah. Anyway, so that's the overhead. So it is the overhead, and every time you call a function, it's got to push the frame and remember things, and unpop and so the stack makes sense because you keep pushing. Every time you push something that is basically in cryo state, it is not going to be unthought until the stuff on top of it has been unthought, and that's not going to be unthought until the stuff on top of this is unthought. So everything is in cryo state, right? And stack is perfect for that because it's the last thing in is the first thing out. That is the only thing. So you have a vector where you can access anything, and you say, I'm going to put a brick wall in front of the vector. You can't access the whole vector. The vector is too damn powerful for you, right? So I'm going to give you a no frills version of the vector where you can only access one place in the vector, and that's top, right? So that is your stack. All right, let's go ahead and I don't know if this is a segue into stacks and stuff, but we'll go ahead and now, and that's the reason when you do function, and that's also the reason why the function signatures are so important, because when you say that a function, okay, when you in your function signature, if you say the function takes a double, right? If you say a function takes a double, and then I don't know, it'll get promoted, right? So let's say a function takes an integer, right? Function takes an integer, 4 bytes. Function takes an integer as a parameter, and then when you call the function, you pass it a double or something like that. I don't know. I've got to play around and find out. So meaning the function signature where you say a Nate function int n, right? And then when you call it, you call Nate function 3.141, right? So it's a double or something like that. I don't even know if that's possible, but if it passes, what happens is that that is a serious issue, because when Nate function starts up, it's going to look for only 4 bytes, right? Because it needs an integer, but it's been given 8 bytes. Because what was pushed on the stack was 8 bytes, but the function itself only knows to pop 4 bytes because the function takes an integer parameter. It's a very subtle point. Chime in here and let me know if that is too much. It's a subtle point, but it's very important, because if there's a mismatch between a function being called, the number of bytes that are being pushed on the stack, because when you call it, you're pushing stuff on the stack, right? The parameters, and the function is actually running when it pops the thing off the stack to say, hey, what am I being given to do, right? What the function pops off the stack is defined by the signature and everything. When you created the function in C++ and so on, the compiler defines the function to say, okay, this function needs a double, so it's going to pop 8 bytes off the stack, right? It's going to pop 8 bytes off the stack. But when you call the function, you only passing an integer. That's 4 bytes, right? So and then the caller is perfectly happy. We'll push 4 bytes and say, all right, I'm going to call Susanna, right? Or Nate or something. And this function says, all right, according to the source code, I am supposed to be passed a double, right? And pops 8 bytes of the stack. So what happens there? What happens there is your entire program will crash, because it popped the 4 bytes that were given part of the integer that was passed, and also for 4 more bytes because it thinks it was passed a double, right? And where do those 4 bytes, the extra 4 bytes come from? The extra 4 bytes come from the return address, right? Which was also pushed on the stack before those 4 bytes. Yes?
Yes.
So your return address just got clobbered. So when you're done doing your stuff and you're going to say, all right, let me go back to Susanna and tell her that I'm done, you're going to try and pop the return address, but 4 of those bytes, 4 bytes of your return address are already gone. So what you're probably left with is, the trailing 4 bytes and 4 bytes of something else of Susanna's stack frame. You pop that, and all crazy kind of shit happen after that, right? Because you don't even know where you're going, right? You get a random address. You don't even get Susanna's address, right? So that's why function signatures are so important. And that's why in C++, a compiler complains. When you say, when you call a function with an integer and the function is actually defined to take a double, the compiler will complain and say, hey, doesn't match the function signature. Yeah, have you encountered that error so far?
Yeah.
Yeah, okay. So that's what it means. That means the compiler is looking out for you. It says, well, I can compile it if you want, but at the runtime, the runtime system is, you have 2 parts in your program. One part is going to try and pop 8 bytes. The other part is trying to push 4 bytes only, right? And then, there's no saying what's going to happen, so I'm not going to translate that into code for you. That's basically what your compiler is saying. Is that a reasonable primer on stacks?
Yes. Yeah, pretty simple for me to understand.
Hey, Chad, yeah. You've been, vocal before. So, yeah, someone. Someone else.
I'm just going to leave it someone else.
Yeah.
I think I kind of understand, but it's still kind of going a little bit fast. I don't know about everyone else. But-
I'm having the same problem.
Yeah, it's a little bit fast to
I
comprehend.
see. I see. All right. Well, let's implement it. Let's implement it.
Okay.
I agree. I think once we implement it, it'll be easier to see.
Yeah, it just turned out into another huge spiel. It turned out to be another huge spiel because nobody interrupted. So it's your fault. All right. Okay. All right. Okay. Good.
I
It's
learned
maybe I'll
somewhere
just
I
all
wasn't supposed
make
to interrupt
sense.
my professors, but
Yeah, not the case with me. All right, you should basically just feel free to interrupt anytime you want. Okay, all right, good. So let's go implement stack class and say in stack.h. Let's also make sure that your stack.h file is not going to be included more than once. So let's start with the preprocessor directive. So hash. So let's say hash if and def hash one. You know the pound sign hash.
Pound sign.
Yeah, hash if and def. Right, it's a preprocessor directive, not even part of C++, right? So yeah, don't worry about it. All the stuff your IDE should fill in for you normally.
Is this correct?
Oh, if and def.
And not def, right? And if and yeah, if and def, yeah. Space stack all uppercase stack _h. Okay. Also h also under uppercase. Yeah, we'll keep the same convention. Okay. On the next line, say hash define stack _h.
_h.
Yeah, whatever. No, stack _h.
Okay.
What I'm saying is that when you include this file, check if stack _h has a definition. If it does
Okay.
not have a definition, then define it. Basically, define it with nothing, right? Just define it, and then do your magic. And at the end of the file, right at the bottom, hit and enter a couple of times. Yeah, enter a couple of times. One more time. Yeah. Say hash endif. Hash endif and no end if
Oh.
and if no, you got to be hash end if
End if.
endif ENDIF.
Oh, okay. Sorry.
I think you got an if at the beginning, so you got to get rid of the if. Yeah, end if. Right, and I think what you can do is at the end of a couple of spaces, and then open a comment there. Open a comment. No, on the same line as the endif, because sometimes the files get really big, and then people forget what the preprocessor directives match up to. So what people do is at the end you say what this matches up to is stack _h. So you say stack _h right there. So what that means is that when this file gets really big and someone encounters the endif and says, hey, what if does this endif match? They know, okay, well, there must be an if up there in the file that deals with that. So that's what it matches. Now, the body of our function of our entire file is going to go between the two in that black space you've defined. So go to line number 4. Line number 4.
Mm-hmm.
Yeah, line number 4, and say class stack as an uppercase S, and then space stack lowercase tack. Yeah. Okay, and then space open brace and close. Yeah. Okay, and then take the brace to the next line, the closing brace to the next line, and put a semicolon after it.
Oh no.
Yeah, semicolon after it, and then we can define the body of the class inside of here. Okay, so our stack class. Let me see. I'm just thinking off the top of my head. All right. So let's say we'll define some private methods and some public methods. But let's just do the public methods now, and we'll fill in stuff, right? So I'm just I'm pulling code out of thin air here. Okay, so say public colon, yeah, colon. All right, what do we need? First, we need a constructor, right? So let's say on the next line, say stack. The constructor is basically a method with no parameters, right? No parameters and semicolon. Yeah, semicolon. Yeah, semicolon. A semicolon right there. And on the next line, let's say we also want a destructor. Right. So let's say, do we need a constructor? Yeah. Okay. Let's do a constructor and a destructor. Yeah. Let's do a destructor. Right. Let's do a destructor. So destructor should be tilde, and then the same name as a constructor. These are two special methods, right? Two special methods that get invoked every time an object is created and an object is destroyed. So you'll encounter these, right? Tilde is I think, what is it? Shift. Someone tell me. Shift back tick, right? It's above the, above the tab. You look like you're on a Mac, right?
Oh no,
Step
I'm
up.
in my PC.
Oh, you're on a PC?
Shift above tab.
Yeah.
Shift,
And
shift
then
tab.
tilde, the squiggly.
Oh wait.
I think it's above the tab sign. Under the escape
Oh.
of tab for me.
Oh, okay. Is that?
Yeah, that's the one.
Oh, I
And-
forget it's called a tilde. I was like
And
so
then yeah,
confused.
no space after that. Just say
Okay, no space.
conventionally, just say stack, and then open close. All right, so those are your two special methods. We'll come to this later, right? So those are two special methods that we have to define. They construct and destroy your stack, right? So, and then the utility methods that we want for our stack, the public utility methods, right? So give yourself a blank line after that, a blank line.
Okay.
Yeah, a blank line after the destructor. One more blank. Yeah, okay, good. No, yeah. Well, yeah, okay, now indent in. Now, here are the methods we want. We want a method to tell if the stack is currently empty or not, right? And it should say true or false, Boolean, right? So say bool, space, is empty. Empty. And then open close, that's a method. Basically, we're going to define this method. And then does this method need to change the object? No, it's only going to examine and tell you something, right? It's not going to change. So let's make sure that this method is a constant method, meaning that it's going to tell you something, but it's not going to change the underlying object. So you can tag this method before the semicolon, say space and then const. Lowercase const, yeah. Yeah, okay. All right. So
after the semicolon?
No, before the semicolon, right?
I meant, oh no, I meant after parentheses.
Yeah, that's what you did.
Cool. I mixed it up, that's why.
Yeah. All right. So next line, other methods we want, right? So we got, is it empty or not? Then we want to know what is the top value of the stack without changing anything. You want to know what the top value of the stack is, right? So let's say, let's make this a stack of integers. Okay, let's make this a stack of integers. Change the name of the no, don't change the name of the file. Okay, or the class name. So, but above the class, make a comment. Saying a one-line comment saying stack of integers. So we know we're just doing a stack of integers, right? Or stack of strings, right? Stack of strings. Okay, putting a blank line before that so that it's attached to the class and not to the preprocessor directory. Okay, great. So bool, right now, so on the next line, so we want to examine the top of the stack. We say string. It's going to return a string, right? String space top. And then also that is going to be a const method. It doesn't change the stack. It just tells you what's on the top of the stack. So they say const. Yeah. Const. All right. On the next line, now we want two more methods. One of those methods is going to take a value from you and push it on the stack. Right. Another method is going to take something from the stack, change it. Right. Change it. Take the top guy and give it to you. Right. So two more methods, and these two methods are going to be called push and pop. Right. So let's say, no, this push should not be a string method. So push, what push should do is that it takes something from you and pushes it on the stack and tells you whether it's successful or not. Right. So let's say bool. Right. So bool push. Right. Bool push.
Is it
Yes,
also
please.
a const or no?
No, so this bool push, but it takes a parameter, right? It takes a string from you and pushes it on the stack. So it takes a string parameter, say string space s, right? Yeah, so it takes the s. No, that's it. Okay, space s, right? So it takes a string and pushes it on the stack. All right. So and it's not a stack. And pop should basically just pop a value from the stack and destroy it, right? And if the stack is empty, it returns false, right? It doesn't do anything. But if it's not empty, it does its thing and returns true. So pop also is a bool. It doesn't return the thing that is popped, right? It returns, and there's a reason for that, right? There are many interesting and rich Reddit posts in our subreddit, or maybe in 2B, I don't know, right? Where we talk about whether methods like push, pop, pop especially, right? Pop and DQ and so on should return the item that was obtained from the operation, right? When you pop an item, you popped it and you got it, right? Should you return that or basically throw it away, right? And all common sense says, mostly, right? It says, well, you took it off the stack, now give it to the user, right? But we found through experience, and it's, again, this is a very nuance, right? Subtlety that you have to research and find out why. Through experience, we found that even though you took something off the stack, it doesn't make sense to give that to the user, right? You take that off the stack and throw it away. So pop should not take it and give it to the user. Pop should take it and throw it away. The only way a user can get something on the stack is to leave it on the stack without popping and have top tell it what's on the stack. So that object is still alive on the stack and top can interact with the object, right? But when you pop it, it's gone. Does that make sense?
Yeah, and I think there is I think I did this in my quest state, but I think the reason why you have an argument string is so you can get it, right? Get the top before removing it.
I'm not 100% sure, but I'll believe you. I'm not sure that Quest 8 has this, but yeah, maybe it does.
Yeah, it does. Yeah.
Okay. All right. So that is the reason why in many data structures, not just tags, when you're have a collection of items, and when you say remove an item from the collection, the removed item is not given to you. Right. And lots of beginning programmers will say, no, even on Stack Overflow, right? If you go on Stack Overflow and ask, lots of beginners will answer the question saying, no, why waste cycles? You've taken it off the stack or taken it from the collection, give it to the user. Maybe they can use it, right? Don't throw it away. And there's the truth is that there's more arguments for the other side, more arguments saying if you give it to the user, more likely to cause problems, right? Throw it away. Better for them to say, I can only use the item if it's already there in the collection. If you've taken it out of the collection, you can't use it anymore. So that's the argument, and it is a very solid argument, right? And lots of people don't know that. And then they'll say, when you pop something, you should give it back to the user. No, that's the, and again, when you go back, when you do these advanced courses and upper division courses, you will still, I bet you'll have classmates that say, when you pop something off a stack, when you DQ something, you should give it back to the user. And you can tell them, no, this is the reason why you shouldn't give it back to the user. You don't know if the object is alive or not. When it's been taken out of the collection, maybe it's been killed, right? You can't interact with it anymore. So you don't know, you don't have control over that, right? Yeah, especially if it's a template class. If it's a class, it's very general purpose. You can allow users to put any kind of thing on the stack, right? Players, entire movies, right? So if it's a general purpose collection, you can't take the liberty of taking something off the stack and giving it to the user, right? It may be a really complex object, and the moment you take it off the stack, it's destroyed, right? Self-destroyed, like Mission Impossible, right? Bam. And you can't give it back to the user anymore. So you can't take that liberty. So when you get more experience, you'll say, well, it makes more sense not to give it back to the user now. Right? Okay, I think those are the only methods we need. Right? So do we need anything more? Okay, so those are the only methods we need. Now let's go ahead and implement some of the private stuff, right? So there's some of the private stuff that we're going to use in order to provide these methods to the user. Okay, so so here's how I'm thinking of a stack. What time is it, by the way? Oh, we got a lot of time. We got a lot of time. Okay, so I'm thinking of our particular stack, right? So when you create a brand new stack, an empty stack, inside of a stack, you have a little cell. Okay, so all our data, all our strings, every piece of data we store is going to go in a little box that we put on a stack, right? Everything the user gives us goes in a box, and that box goes in a stack. But in that box, you have the thing that the user gave us, and also one more thing. What's that one more thing? The one more thing is going to point to the next guy in the chain, right? If it was a vector, if it's an array, you don't have to worry about this, right? Think about it. If you had an array of objects, you don't have to worry about the sequencing. Yes, you don't have to tell who's after me, right? So because it's 1, 2, 3, 4. The sequencing is implicit in a vector. Yes or no?
Yeah.
Right. So that is the incredible power. That's the incredible power of a vector. But here we're saying we're going to challenge ourselves and do things the harder way, right? Just because we want to do things the hard way, we're going to do things the hard way and say, no, we're not going to use the automatic sequencing given to us by a vector. We are going to do the sequencing on our own with random memory locations, right? Not like a vector where the memory locations are one after another and I can just use sequencing. I'm going to use random memory location. Every cell I get is not cells in a vector, but this cell might be here. Another cell when I get ask the system for it may not be the next place, maybe somewhere here, okay, another cell here. So each time I want a new item to be pushed on the stack, I'm not going to take the next cell in the vector. I'm going to ask the operating system, give me more memory, give me more memory. So it gives you lots and lots of boxes. These boxes are not one after another. These boxes may be all over the place in memory. I don't know. These are depending on the operating system. They may even shuffle these things around, right? But the only thing it guarantees is that I'll give you different boxes, right? And each box will have a space for the string, and it'll have a space to point to the next box. So far, does it make sense? It's a very important concept because it's important to piggyback on to the next one, right? So tell me if you have any difficulty at all so far, saying that all the information is not going to be stored in a vector, but instead it's going to be stored in boxes, in which in the box I'll have the item, plus I'll have the address of the next box, right? So these boxes don't have to be next to each other. They can be anywhere, but as long as it's a chain, right? Which points
Oh,
to
yeah, that
it's
makes
just like an
sense
array.
now.
It is just like an array because I have the sequencing information, but the sequencing information is built in those links that I built, right? From this box to that box, that box to that box, that box to that. So if I build a chain, then I have very similar to the vector, I have a chain, right? Very similar. I have the sequence 1, 2, 3, 4, 5, 6, 7, 8, right? But the chain is not because of contiguous memory locations, but it's because of these links, right? That point, right? But by traversing the links, I can still have all of them in a particular sequence, but it's not stored next to each other. That is a critical concept to understand and get past. It takes a little while, so I can wait here for a little while if you need that to basically, brew on a little bit, right? And find out, but it's very important to understand, right? The difference between a vector and a list, a linked structure, they're both sequential data structures, sequential, and they're also linearly sequential, right? Linear meaning each one only has one successor and one predecessor, right? Linear, like a line, bam, 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 bam. A line can curve, but it's still a line, right? If it's non-linear, then you're screwed, right? Because one, like Fibonacci, 1 and then 2, right? Each of those 2 go in 2 more, right? Is branches. And this is like a tree and a graph, and they can interconnect. It would be spaghetti, right? So non-linear is messy, but both of these are just perfectly linear data structures. The vector is even more simpler than the list because it's all ordered to, all in contiguous memory locations. You can go one after another. The list or a linked data structure, they're all in boxes. They're all over the place. Each one has its pros and cons, right? A vector, the pro of the vector, the benefit of the vector is that the sequencing is really fast, one after another, bam, 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 like that, right? It's really fast. But the disadvantage there is that it has to occupy a contiguous block of memory, right? So if you have badly fragmented memory, right? So you got like 5 terabytes of memory, but you don't have 100 megabytes of contiguous memory. That's possible, right? Because you can have badly fragmented. I got lots of memory, but I have lots and lots of data, right? Then what you do is, do something like disk manager, not disk manager, memory manager, right? And to compact things out, right? And say, all right, so let me take all those pieces and put them all in one place. So I have, a contiguous free space of lots and lots of memory, right? So if that doesn't happen, you have a lot of memory, but it's all fragmented. Yes. So if you fragment it, then you cannot have a big ass vector. Yes, you can only have a big ass vector if you have lots of free space. But if you have lots and lots of memory, but fragmented, you can't have a vector. So
Professor,
then, yeah.
The reason is because underneath vector, it's actually implemented using like an array. So
Yeah, exactly.
Right?
A vector is essentially an array, right? A vector, it's a vector, an array on heap.
Yeah, and once it's actually reached its limit, meaning like, let's say it originally created 100 elements of the array. Once it reaches the limit, then it has to create a new array to copy that stuff into a bigger array, let's say double the size or triple the size. Yeah. And then it copies the original stuff over. And that's okay. And then when it
most
creates
of the time, that's absolutely right. Most of the time, in modern machines anyway, what happens is that when you want to grow the array, there's usually the original array was placed in a place where it's very unlikely that you'd have to move the whole thing, right? You'll still be able to grow
I see.
right there.
I see.
Yeah, so all kinds of calculations happen to determine where the array. We think that compiling is, or even the operating system, right? There's a lot of nuances that go on in the background, including even things that we just take for blind granted, right? So we just say, oh, we got an array, but where to place the array in memory so that the programmer doesn't have to worry about moving around a lot, right? So because most of the time we're not even aware that stuff is being moved around. The operating system takes care of that for us transparently. Yes. Because there's a memory map that the operating system makes available to us, but on the other side of the map, the operating system knows where the different parts of the memory are, right? So you may have an array here that got too big for it and it needed to grow and moved it here. But on this side of the map, the operating system will make sure you don't see any change, right? All of that magic happens here. Yeah? So
yeah, you kind of are going a little fast.
Oh, okay. Yeah. Thank you. Well, you can always feel free to rewind me too. Right? So,
I'll just remind you if I notice it again.
Thank you very much, Chad. Yeah. You can also rewind me, not in the video. You can rewind me to say, hey, we're talk about something.
But yeah, you could say like, if I'm understanding correctly, you'd be okay with us like saying like, could you repeat like the last like.
Oh, totally.
Yeah.
You can tell me. You can tell me. Can you repeat something from 5 lectures ago? I'm happy to do that too. Yeah. That's okay with me. Yeah, because I know, right? I'm not one of those people where like when I was a student, there's lots of things when I understood in lecture number 15 that I did not understand in lecture number 5 at the time of lecture number 15, right? So even when I understood stuff that was going on, I still didn't understand some of the stuff that was talked about early on. Yeah, so I'm pretty sure there must be students like that. So if you didn't understand something before and it's still relevant, yeah, I'm happy to talk about it. Right? Even now or another time, make a lecture, extempore lecture anytime. It's fine. Today I have meetings in the afternoon, but.
I have a question about linked lists. You mentioned you're linking data structures. What are those data structures that you're linking together?
Oh, yeah. So basically classes we're going to create, right? So in this case, let's create inside of above class, let's create a node, right? Above class, above stack, we're going to create this data structure, right? So hey, Susanna, above the stack of strings, let's make that an outer class, okay? No, actually, let's make it an inner class, right? So inside the stack, above public, right? Above public, inside of stack. Above public, yeah. All right, so let's create a struct there. It's struct, right? A struct is, I think we went over this before, right? I think we went a struct is basically the same as a class in which everything is public, right? So just think of it as a package. It's a package, right? It's a package, and let's call it a node, right? Struct space node with capital N. Yeah, space. Sorry, semicolon, right? Struct. Oh no, yeah, curly brace. Yeah, and inside of the curly brace, we say string space data, the data type string, and then space, and then data. Yeah, string. You got an S there. Strings, not strings.
Sorry.
Okay, so string data, and then what we want to do is on the next line, semicolon. On the next line, what we want to do is that's our box. We're now defining whatever that. Yeah, I think maybe Aaron or Robert asked the question. What is this data? What is this data type that we're storing on the stack? That frame. This is the data type we're going to store on the stack. This is the box. We're designing the box. We're calling this box node. The name of this box is node, and inside of this box, there's going to be 2 things. There's going to be the string that is the data that was given to be put in this string inside the box. The other thing is got to be a link to another box. Okay, so it's going to be node, N-O-D-E, right? Uppercase N, because it's a pointer, right? After we type it in, I'll explain, right? And node with a capital N, a node with a capital N, node, and then node dot, right? Space, star, and you have a dot there, right? So get rid of the dot, node, node, star, space, star, and then say next, right? And no space there, node star next. Okay, semicolon. Okay, all right. So what that means is that node is now a box that's it, right? That's it. End it, right? So we've got a data structure. This is a class. It's a class where everything is public. Right? This is just a bag, right? We got a box in which there is a string that can hold data, and there is also an address. You know, star is basically node. Did we go over the concept of pointers at all before?
No.
I don't think we'd have.
Oh, okay. All right. Okay. So a star is an operator. You know, as you know, it's also a times operator and a comment operator and all, right? So star also has one more meaning. Star is called the dereference operator, right? Dereference, D-E-R-E, dereference, right? Referencing and dereferencing. Dereferencing. What it means is that if you take a variable and store it, star P, right? Star X or star, you know, and P is a variable, star P, right? Is the star operator applied to the variable P. That means that interpret P as a memory address, okay? Interpret P as a location, go to that location in memory, fetch the contents of that location, and that's what star P is. Does that make sense? It takes a couple of days, okay, for this concept to completely sink in, but you have to be aware of that. And I find that just because it takes a couple of days, finding out about it now and knowing it's going to take a couple of days, I come back to it in 2 days' time, and then it'll make sense, does not work, right? It means it takes 2 days of thinking about, which means it may not even be 2 days. Those 2 days of thinking may occur over 2 weeks, may occur over 2 months, maybe it even occurs over 10 years, right? But until that concept sinks in, you cannot make progress in C++, right? But fortunately, this is not a difficult concept, but I think it's on average, it's about 2 days. It takes about 2 days to get completely comfortable with this concept, saying it's a dereference operator. When I say star P, it is the same as going to the location P, getting the contents, and replacing the star P with the contents. Does that make sense?
Yeah, so it's essentially a pointer, in other words, right, to a different
Yeah,
address.
yeah, yeah. We're talking about pointers, Chad.
Yeah,
I'm
we're
trying to
talking
explain
about
what the pointer is.
pointers.
Cool. Yeah, that.
No, yeah. You know what the pointer is. You said you know what the pointer is, right? I want to know if other people who find it confusing, what was this helpful, and are you feeling that you're getting closer to this whole idea of pointers?
I think so.
Yeah, it takes a while, right? But you have to keep things coming back, right? You may forget about it and then come back, right? And then again struggle with it for 10 minutes, right? Go back, and forget about it. But you have to keep doing this because it is the net total amount of time that you have spent thinking about it, right? It needs to be somewhere around 2 days to get 100% comfortable with this, right? So, but if you say, I'm going to think about it occasionally, it'll take you correspondingly longer, but you have to keep coming in the beginning. It will always be, and we'll do a couple of examples, right? So in fact, go back to your main, click on main. I'm just going to just click on main, click on main. Yeah. All right. In your main, say int n equals 10. In your main, do int n equals 10. This is a really quick experiment here. Okay. Int n equals 10. Int n equals 10. Yeah, okay. On the next line, say int star p, on the next line. This is an experiment, okay? You guys can try it out, right? Int star p.
Does it equal anything?
Int star p equals. Now, int star p, what int star p means is that star p, int star p means that star p is an integer. Okay, because if you say int x, x is an integer, yes. If you say int x, int n is an integer, yes.
Yeah.
Okay, so int star p, right? Instead of n, you have star p. That means star p is an integer, yes.
Yes.
Okay, now if star p is an integer, yes, you have to follow this, right? If star p is an integer, and star is an operator that goes to a memory address and fetches that thing. Whatever that was fetched was an integer, yes?
Yes.
Okay, all right, which means that P is actually an address that stores the integer, yes?
Yes.
Okay, which means that P is a memory address, not an integer itself.
Ah.
Okay, so P could be like, P could be 1, 2, 3, 4, 5 El Monte Road. It's not an integer. P is an address, but star P is an integer. So that's what it means. So that's what, there's a very subtle nuance there. It's all very short, and it's like 5 characters, right? Int star P. But there is a tremendous amount of subtlety hidden there that it takes a while to understand, because there's so much hidden in there. The star P is an integer, but P is a pointer because star P is an integer. Yeah. Right. So now it takes a while, right? So I hope you can record this, right? Or remember this. Remember this, because now it seems so mystifying. And the incredible thing is that in 3 weeks' time, right after spring break, assuming that you've been working on Quest 9 and so on and get into 2B, after spring break, you would not even be thinking about it. This would basically be like walking. Right? You would say int star P, player star P, and a double star, triple star. All of these things are pretty much damn straightforward to you, right? And in order for that to happen, that's what I mean, right? You got to get used to it. Now, once you get used to it, it's an incredibly powerful tool, right? Imagine now you can see the enormity of the power behind these 5 letters. You can see it, right? Very soon you can't see it anymore. You cannot see that. Very soon they'll just be 5 letters to you. Right? Now you can remember that and say, that is the power I'm bringing to bear, right? Very soon there are 5 letters, but they have a lot of power behind them. Lots of people don't see the power, right? So, but once you see all that, you can see, all right, the power is, oh, that's the power of the pointer. That's the power of something on the stack. That's the power of something on the heap. That's the power of the vector. That's the power of a queue, right? And you can bring all these things to bear, and you can craft these incredibly nuanced and subtle solutions. Because to chip away at the fine details, you need fine tools. And I was thinking about this yesterday, because many times in modern manufacturing, right? So many times in modern manufacturing, in fact, even if you go to some of these ancient sculptures, right? So incredibly beautiful sculptures. And we always think about sculptors working on these sculptures, or machines being made and people designing these parts. Actually, with some of these more modern technologies, it turns out that you spend a great deal more time designing the machine that is going to design the part, right? So if you want a particular kind of die to be cast, you spend a lot of time engineering the mold in which the die should be cast, like the 3D printer, whatever it is, right? Like in software, you spend a great deal. Right now, testing things is really simple, debugging. But later on in the life of your software career, you'll spend a great deal of time, maybe even 25% of the whole software development effort is spent in constructing very, very clever tests. Now, tests themselves may be so involved, so critical, so ingenious tests, right? Ordinary engineers can't construct these. So these tests have been fabricated so nuanced. So as these chisels have been, these very specific chisels, they themselves have to be machined, right? You can't, in order to construct this piece, you need a particular kind of chisel. But in order to make that chisel, you need a very advanced numerically controlled machine, right? In order to make the numerically controlled machine, you need software, right? So all of these build on top of each other and finally get you the finished product. And likewise, you'll find, right? Even I don't know how we got started talking about that, but pointers, right? You bring these power, you bring all of these tools to bear, and then you can create these incredible products, right? So int star P, now you can say int star P equals int star P before the semicolon, you say equals address of n, right? Address of n. So ampersand is the other operator. And today, obviously, it is supposed to be pointers, right? So we are talking about pointers. And obviously, next class also, we can talk about, the stacks using these pointers, and then take that over to the list, 2 lectures, more than enough for all of that, right? All right, so int star P equals address. So what that says is that n is an integer, okay? And it's equal to 10. P is a memory address, and the memory address is the same as the memory address of n, because address ampersand is address of, right? Just like star is the opposite. E to the x and log x are opposites of each other, right? Like that, ampersand and star are opposites of each other. Star takes the contents off, right? Ampersand takes the address off, right? So address of n means, go to the place where n is stored in memory and get the address, right? And take that address and assign it to P. Now, P is the same address as n. So if you change n, the contents of P also changes. Now you can do a bunch of experiments, right? So underneath, you can say cout double less than n, right? So yeah, until cout and then n equals within quotes you can say n equals yeah, and then double less shift left shift yeah endl and you need an endl. Yeah, and then you can copy and paste that line 4 or 5 times. You can say address of n. By the way, it needs to be lowercase n inside of the quotes. You got uppercase.
Why do we use pointers to get the address of a variable instead of just dynamically or just getting it every time we want to get it? Like, I don't know, couting and n.
I'm sorry.
Basically, why do we use pointers instead of just like
Just using n directly. Yeah, no, in this case, we're using it in this particular case. It is a very contrived example to show you what here's an integer and here's a pointer that's the same as an integer and so on. Normally, you don't do this. Now, when we go to our stacks, we're not going to be using pointers like this. We're going to be using pointers to point all the way out of there, right, into something else.
Okay.
Yeah,
I see. So outside of the class, I get it. So
you can get it to point anywhere you want.
Okay, cool.
Yeah. So here it's a very controlled situation where we are trying to, right? So yeah, n equals, and then you can say on the second one, you can say ampersand n equals ampersand n. So the address of n equals address of n, right? Address of n equals, and then here also left shift address of n. Yeah. Okay. No, left shift address of n. The left shift. Here. Yeah. There you go. Here? No, left. More to the left. One more. Yeah, no, to the right. Before the n, turn the n into ampersand n. Yeah, I think that's what I should have said. Yeah, okay. And then copy and paste one more time. Do the same thing with p. You say p equals this, and star p equals that, right? P equals that, and then star p equals that. No, p equals p. P equals p, and star p equals star p. Yeah, and then star p equals. Right, so you got these 4. Now you can print these out, and you can see what the values are, right? And in fact, you can look at the addresses in the replete machine. We don't know where it is, right? So I think we can actually compile and run it now. You can compile and run it, and you should be able to see 4 lines, right? So you have n equals 10, which is correct, yes? Yeah, and yes. Then look, so address of n. So n is actually stored in memory. Right, n is stored in memory at that location. That is a memory address, right? How many bytes is that? I don't know. That's maybe a 64-bit machine, right? So 8 bytes, 8-byte machine, right?
Yeah.
A 64-bit machine, right? So
I mean, most stuff 64-bit now, right?
Yeah, mostly, right? So that's a 64-bit machine. That's a memory address, right? And then P also is the same memory address. Look at that, right? P is the same memory address, right? And the contents of P is 10. Because the contents of P is the same as the contents of that memory address, which is the same as the contents of the address of n. Does that make sense?
It's kind of similar, so I'm having a hard time understanding it, to be honest. Kind of similar to n.
Yeah. So basically what we're saying is that P is a pointer, and the value of the pointer is the address of n.
Oh, yeah. So
P is an address. P is an address which is the same as the address of n.
Oh, yeah. So that will play an important role in linked list.
That will play an important role in linked list. But does everybody understand this so far? Right? I want to know.
Yeah, I do. It's just the pointer thing seems similar.
I'm happy to continue implementing the stack with Susanna. We can continue to do that, or we can spend more time on this if you want, and keep that.
We try continuing to implement because that'll probably help me understand what's going on.
All right, but one more person than you. Hey, yeah, not just you.
One question.
Yeah.
If we did star and n, would that return the value of n? Because on line 17, what is that in relation to n? Is it star and n? Is that equivalent to star p?
No. So p is address of n, ampersand n. Yes, p is the same as address of n. Yes?
Yeah.
Okay, so star p is star address of n.
Yeah.
Because so p can always be substituted by address of n here.
Okay.
So star p is star of address of n. What address of n is the address of n, right? So star of address of n is the contents of the address of n, which is n.
Okay, so star and n is the value of n.
Yeah, star and cancel each other out.
Okay. Okay.
Yeah,
Okay.
because
thanks.
it's like, you know, a log of e to the x is x. Yes.
Yeah.
Or e to the log x is x. So they cancel each other out because star says, get me the contents of an address, right? And ampersand says, get me the address of the contents,
Okay.
right?
Okay.
So star of ampersand of contents is nothing but contents, because star of ampersand of contents is star is the contents of the address of contents. I don't know. Yeah, like I said, you know, it's just like I talk for 2 days. Whether I talk or not, it's going to take 2 days, right? Whether you work or not, it takes 2 days, like that. Whether I talk or not, it's going to take 2 days of your thinking about it to get to grips with this.
On line 9, then, do we have to have the star before P? Or would it?
Yes, because if you don't have the star, it won't even compile, right? Because try it, take out the star and try and come here. Modern days, you should just try things out, right? Try it out, get rid of the star and compile it. It'll complain saying, oh, you're trying to assign an address to a plain integer, right? It won't work. The compiler should complain, right? Go ahead, get rid of the star and try to compile it. Go to line 9. Susanna?
Line 9?
Yeah, go to line 9.
Yeah.
Get rid of the star, right? It won't compile, right? Oh, just mouse over the red, you know, it'll tell you. Initialize a variable of type int with a value of type int star, right? Because address of n is the address of n, right? An address is a pointer. It's an int star, not an int. So you're trying to take an int star and trying to put it inside an int. So the compiler is not going to let you do that. Yeah.
Okay.
That's why you got to have the star.
Yeah.
So what that says is that contents of P is an integer. P is not an integer. P is an address. The contents of P is an integer. That's what it says. The star says contents of P is an integer. So you got to put the star back.
I see. Right. Thanks.
Yeah.
Got it.
Yeah. Hey, put the star back, Susanna. So anyway, it's good that this is on Replete and it's being shared and all, right? So yeah, and it's recorded, so you can experiment more ad nauseum with this. We can go back to the stack class now and continue to flesh it out more. Unless you guys have more questions, you want to stick with this more, that's fine with me, right? We never got a chance for you to keep driving like last class, unfortunately, which I wanted to do. But I think we can do that next class, earlier on, because we've done a lot of that stuff now, right? So you basically go ahead and after 10 minutes into class, you can start playing next class on Tuesday. By the way, week 11, I think, is when you guys have to start nominating the most helpful member for the $250 prize, right? So you got to send me email. I think maybe I'll make a Reddit post, or a Canvas post reminding you to send me email nominating someone for the most helpful member. And then I'll set up a poll somewhere towards the middle or the end of week 11. And then you can go and and the winners, I'll pay the money. So you got to, maybe you have to declare it on your income tax returns as income of some kind, right? Income or scholarship, whatever it is, you have to declare it, I think. You don't have to give me a receipt. So. All right, so let's go stack. Are we good with implementing a stack now? Can we go ahead with implementing a stack?
Yeah.
The chat, you can't answer, okay? So because you're always interactive in class, let's just say for the rest of this quarter, you're not going to speak up, okay?
Cool. Okay, I'm just going to stay quiet and listen.
Yeah. All right. Good. Thanks. Hey, guys, are you okay with this? Can we go ahead and implement a stack, or you have more questions to do with pointers? Want to feel more comfortable with pointers?
Yeah, let's do it.
Yeah, let's.
All right, let's do a stack, and then we can go back to pointers too later on, okay? So now in my private section of the stack, what I need is basically, right? So do a private section right there. Private and colon. On the next, so what we want to do is, let's say at any time, I want the top of the stack to point to what I have out there, right? So let's say I have a node, node star top underscore stack, right? Let's say node. So this got to be. I'll talk you through this and then I'll explain, right? So
Okay.
say capital node, right? So it's same as a type. It's a type of different. Yeah, node space star top underscore off underscore stack. OF, a single F. Yeah, single F. Top of stack. Okay. So what that means is that I have a private variable which is always pointing to a box. You guys have to be in step with me and tell me if you're not in step. Okay. Inside my stack, you can't see it because it's private, but I have a variable. I have a variable, private variable inside the stack, and it is always pointing to a box. Okay. And in that box, either that box is null, which means it's not pointing to a box at all, right? We'll come to that later. Or if it is pointing to a box, inside that box, I have a string and a continuation that tells me where the next box is. So far, are we clear? Okay, I need to hear a resounding clear yes from everybody. Yeah, okay?
Yes.
Yes.
Okay, so that's what this means. So in my, I have a, so in my, so let's now go to the constructor. So look at how few variables we need to get the stack actually going, right? So in my constructor, we can define the constructor. So go under the to line 27, line 27. And here we're going to define this constructor, right? So say stack, so just stack, so stack, double colon, yeah, double colon. No, not semicolon, double colon stack. No, colon, not comma.
Sorry.
Shift on, you're fine.
Yeah, it's fine. Take your time because no, double colon, not colon. Double colon.
Shift on your semicolon.
Yeah, Susanna is getting all mixed up.
Why am I getting so like that? I'm sorry. I'm like
shift,
still really sleepy.
Shift on your semicolon.
Don't worry. I forgot what an ampersand was.
I'm so sorry.
Stack, the name of the constructor. Stack, and then open close parentheses.
Stack, open close parentheses.
Yeah, stack, open close parentheses. Okay, and then open a curly brace. Now you can get your curly brace. You've been waiting for a long time. All right, okay, curly brace, and then go to the next line. Okay, now this is the body of the constructor of the stack. The stack, this makes a brand new stack and gives it to you. Yes? Okay, so this stack is going to simply set the top of the stack to null, okay, to empty, nothing there. Okay, so you're going to say top of stack equals null pointer, right? Top underscore, yeah, equals null pointer, NULLPTR. Okay, now you can look it up later, you can Google it, right? That's all. Right? So in fact, you can condense it into an inline later on if you want. Okay, we just make it on one line or move it into a separate file. All that later on, you can do these cosmetic details, tweaks later yourself later. Okay, what that says is that when someone wants to create a brand new stack, I'm going to give them this object called a stack, and inside of the stack there is a pointer which is secret, right? That user can't see. I've just given them something called a stack, but inside there's going to be a hidden pointer called top of stack, and that pointer for a brand new stack is going to have the value 0, okay, which means it is a special memory location. Null pointer, NULLPTR, null PTR, right? You can Google that later on, right? You can look up the value. Null pointer has a special value. That value is 0, right? Now, null pointer is actually an address. It's an address that has a value 0. What does it mean? That value 0, null pointer null, right, is memory location 0. Right, which means it is not any one of the 4.5 trillion terabytes of memory you got on my phone or anywhere on a massive machine, right? I have terabytes of memory, right? Each one of those memory locations has a proper address, right? 1, 2, 3, 4, up to 4 terabytes, right? But none of those have that special memory address, which is 0, right? So I'm going to take away that 0 from all of you guys. Okay, that's what the runtime system says, right? So that special location 0 is going to be taken away from you. You cannot use that in your programming as a place to store your own value in. you can use that as what is called a sentinel, which means that when you want to return something that is illegal, you can return the memory location 0 because that can be used as a universal sentinel. So memory location 0 is a sentinel. Okay, it's a pointer sentinel, meaning that lots and lots of people, you down the line, when you start coding lots and lots of pointer functions, you're going to be using null pointer as a sentinel. It's a useful sentinel, meaning that you're going to return that. You're going to play with that sentinel saying it's an illegal value, right? You can't store anything in it, but you can pass it around as an illegal pointer. Does that make sense? It's a very powerful thing, right?
Yeah.
And it's even better than that because it's not only a sentinel for you, because it's only one memory location. The runtime system can monitor that very frequently, right? It can always very frequently check. If there's only one memory location, it can check. On the other hand, if there are lots and lots of memory locations, 4 terabytes of memory, it's not feasible for the runtime system to check everything to look if it's illegal or illegal, right? If it's allocated to you and you're accessing, or if it were allocated, you freed it and then you're accessing it, it needs to go and check. It's not feasible, right? I mean, lots of them. Whereas one location, it can keep checking very frequently. So if you use that as your fail-safe sentinel, if you write into that memory location accidentally, the operating system will really quickly pick it up, right? And say, wow, null pointer access, your program is going to crash, right? That is good for you, right? Because it was a null pointer, you access it and your program died immediately. If it wasn't a null pointer, what happens if it was actually a pointer somewhere else and it was actually an invalid pointer, not null, right? It was memory location P, but it was not pointing to your N. It was actually pointing to some random junk location because it's long past the time when you used it. Now it has some junk value in it, right? Maybe it's pointing to Susanna's variable in a critical, cardio operation somewhere, right? And it's pointing there, and so that's very dangerous, isn't it? So so that's why a null pointer is a fantastic sentinel there. So in our a constructor, all we're saying is that we're going to have a stack which is empty, meaning an empty stack basically says, my top of the stack is empty, right? So and now is my is empty on the next line, yeah, after the stack class, right? After the class, after the constructor. Let's do is empty there. Well, actually, the destructor also needs to go there, but we'll do the destructor later, right? We'll put the stub of the destructor there, right? We'll come back and fill it in later. Let's because we want to keep things in the right order, right? So put the stub, yeah. So say tilde, the shift, 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 yeah, you got the tilde, tilde stack, all right? Open close, yeah, and then curly, curly, and inside of there, put a comment there, double / to do. Say to do uppercase, yeah, to do uppercase in one word, yeah. If you do that in one word, most IDEs can actually, tag that on the margin, saying, hey, in this huge program, you got these red dots. Those are the places where you got to dos. All right, so to do, and then you can put more there. A complete destructor. Oh, never mind. You can come back to it later. Okay. All right. Now let's do the. All right, now let's do the is empty function, right? So is empty, so bool is empty, and then it's got to be bool stack : is empty. Likewise for destructor also, you got to say tilde stack : stack. Double colon, yeah, and even for the destructor. Yeah, stack. No, you in stack. You need to say tilde stack : stack. No. So on line 31, go after the closing parentheses. Yeah, okay, and type stack there. Type stack. Someone should Google and find out whether the tilde goes before there or at the beginning of the line. I think it's the beginning of the line. No. I think it's get rid of the tilde in the beginning of the line. I think that's a declaration for destructor. Someone should cross-check
that. Looks right.
We'll come to that later. All right. So let's do the is empty. Right? Is empty. Open close parentheses. And then here, all you need to do is return top of stack equals double equals top of stack double equals null pointer. Right? Meaning that if the top of the stack is a null pointer, then your stack is empty. Right? If your top of stack is null pointer, that's going to return true. If your top of stack is not null pointer, it's going to return false. Does that make sense?
Yeah,
yes.
it makes sense.
I actually had a question, by the way, about stacks.
Uh-huh.
Is the reason why we define stacks as a header file because technically it's its own well, I guess it's its own type or data format because you know it's well, as you described earlier, it's kind of an extension of vectors.
It is its own class. Yeah, you're right. You actually
Okay.
you said the answer before. We're doing it like this because its stack is its own class. It's in its own right.
Gotcha.
You can instantiate a class just like that. Bam.
Cool.
But don't forget to remove that tilde on the stack thing.
Hmm?
You see on the is empty, line 35.
Oh yeah. Get rid of the tilde. Yeah.
And it's almost 10, just letting you know.
Okay. Well, you know what? Yeah, honestly, I think we covered a lot of ground today. Did we cover a lot of ground today?
I think we did.
Yeah, I'd say so.
Okay, well, Susanna was typing, so yeah. Okay, well, Ryan already gone. He's already gone. But hey, thank you guys. But I think we covered a lot of ground. We can come back to this code. Hey, Susanna, can you preserve this until next class?
Yep.
Okay, so preserve it, share it on Reddit if you want. We'll come back to it in the next on Tuesday. We'll complete the stack class and then turn this into a linked list, right? Turn this into a linked list, and then so you can play with linked lists also at the same time for 2 lectures. I think we got more than enough for 2 lectures, and then we can also have time for review, right? You also review on week 12 if necessary. Thank you guys so much for today. And I'm sorry if I did all the talking today, but thank you for being patient and putting up with me. Hopefully next class you get to you get to drive this time, right? We'll alternate, maybe something like that, right?
Yeah.
And then thank you so much. I'll see you on Tuesday. Have a good weekend. Okay.
Have a good weekend.
All right.
Thank
See
you.
later.
Think
Very good weekend.
You, bye.
Thanks.
All right, see you.
Bye.
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 Bye.